Hey guys, this is the first part of my video on how to implement the fast Fourier transform, or FFT, for audio programmers. And in this video, we're not going to get exactly to the fast Fourier transform algorithm as much as we're going to look at the basic derivation of how to convert a operation that's traditionally O of n squared into O of n log n, which is what the fast Fourier transform is. And this is kind of the general structure of the fast Fourier transform itself. But we're going to start with a simpler example. And that simpler example is going to be how to solve a polynomial. So here's going to be our function. And we're going to have a constant plus a term times x plus another term times x squared, and then plus another term times x cubed. And as you can see, this is a power of 2, which will come into play later. So taking a look at this function, you have to think about what exactly we're doing here. What happens when I plug in x? And specifically, how does this work? Let's say big O of n y's. What is really happening here? Well, basically, we can think about implementing it. Well, we can think about solving it by just plugging in x each time. So we have, for each coefficient, right, we'll start at the first one. Well, that's just itself. And then we go to the next coefficient, which is 1. So that's just x times the first coefficient. And then, so this is just a big summation, right? And then we have the second coefficient times x squared, and then we have the third coefficient times x cubed. And so we can think of this summation as a for loop. So I'm going to come up with something called, well, not called anything in particular, but we're going to implement this in JavaScript. And these are going to be my coefficients. So A0 will be 1, 2, 3, 4. So these correspond to the subscripts plus 1 for each coefficient. And I'm just going to say function solve is going to take in x and then coefficients. And in here, we're just basically, it's going to be a for loop. So we're going to say for I in range coefficients at length we're going to have some result. We're doing a summation. And inside this loop, we are just basically going to take the coefficient times x to that power. So result is plus or equal to coefficients of a of I times x to the power, so I'm going to just do math.pow, of x to I. Right, because again, this is technically x to the 0. So x to the 0 the first time will be 1, so that's why it's just a plain coefficient. So this is going to give us our result. So if I do, let's see, I just want to log solve, let's see, 4 and our coefficients. If I jump over here, I guess I may need to refresh. Oh, whoops. I is less than coefficients dot length. We get 313. All right, so that's going to be the answer to this particular thing. But I'm going to show you what this really is, because I used math.power. But to get this in terms of big O of n notation, I'm going to show you what power really does and why this operation is actually big O of n squared. Well, basically what's happening is there's another for loop. So I'm going to say var value is going to start off at 1. And then we're going to have another for loop. And this is going to be less than I, right? And now val is going to be times or equal to x. And then this is how the power sequence is going to work. So then I'll say just times val instead. And if we do that, j is less than I, j plus plus. Not sure why, I think it's been live reloading, so it's not great. But as you can see, we get the same value of 313. And so as you can see, we have this double for loop here, which is an issue because ultimately it's going to become big O of n squared, not necessarily lower bounded by O of n squared, or by n squared, but it's going to take two for loops. It's going to take a nested for loop to get that. And so this is not as ideal as it could be. But this is how we are effectively implementing this solve function by default. So this is how we are implementing this equation. So how and what are some ways to make this a little bit better? What are some optimizations we can make? Well, it's a power of 2 for a reason. We know that we can rearrange this equation. I'll give you another example of how you could rearrange this. So let's see, we've got this times x times this plus x times this plus x times 3, right? And this already is a little bit better, but this is not something that I know how to implement off the top of my head. It kind of looks like it has natural recursion, but this is another way that we could do this. But we want to come up with something that's nlogn, right? That's kind of the point of what we're looking for. And so how can we do that? And we can think theory-wise. There's a reason why I chose a power of 2. So basically, we have this equation up here, right? I'm going to get rid of this now because this is just showing you that there are different ways that we could solve the equation. But we're trying to find one that can do it in big O and log n time. So let's think about how we could try that with this. We can think about solving the even coefficients and the odd coefficients. And so what does that mean in particular? Well, let me show you another way of ordering this that might make that a little bit easier. So in theory, right, we want to solve odds. So, well, we're going to f of evens of x, right? I'm leaving a gap here. And then plus f of odds in some way that we can ultimately get down to 2 values, right? This is sort of our base case because we can think about, for example, if we just had this, well, this is a very simple base case. We just have our first coefficient, our even one, and then our odd one here, which is a 1. So we can think about this as being like similar to this. Now, let's think about in practice what we could do to sort of organize this bigger one, like this. And let's try to, in other words, let's try to mimic this shaping here. So something I see is we could take a0 and add a to x squared, and you'll see why in a second. Now plus x, and I'm going to put parentheses around these, and then a1 plus a3 x squared. And as you can see, this fits this general pattern, with the catch that every time we send in whatever to the evens and odds function, we actually square it, right? Which is why we're squaring it here. And if we went a step further in the recursion, if we had 8 terms, then we would actually eventually send in x to the 4th, because we would derive it in a very similar way, where we would take this middle term here, and that would be the first, and then we would add or multiply by x the first time, and then x squared the second time. But this is the beginning of a recursive pattern. If you want to see for yourself, then just do an equation with 0, 1, 2, 3, and then 4, 5, 6, 7, and start with a0 and a4, and try to order it in the same sort of recursive fashion I just did right here. And you'll find that it does, in fact, still hold the same general shape. And so this is a very nice pattern here, because we've just rearranged the order of the coefficients in x. So this is something that's going to evaluate to the same solution, the same number, and it's a recursive function. And we're using this in terms of powers of 2, right? Evens and odds. Ultimately, we're stemming back to 1 even and 1 odd, and then we will have 2 evens, 2 odds, and then 4 evens and 4 odds, and so on, so much, depending on how much or how big the length is of our polynomial equation. Right? So now this general formula is going to help us go from big O of n squared to big O of n, log n. Alright, so hopefully that makes sense so far. This is just a different way of ordering these coefficients, so that we can do this in n log n time instead of big O of n squared time. So to do this, I'm going to have this function called solve R for recursive, and I'm also going to basically solve the same thing with the same number. So solve R for A, and these should be the same. So in order to implement this, we're going to have to get some insight into how the recursion is going to work, because we're implementing it and we got to know all the details. So let's take a look at the general formula that we have derived here. And if you can see, we say the function with evens and the function of odds. Well, that's going to happen multiple times. So ultimately, these values are going to be the most even and most odd values. And essentially, actually, how it's going to work is the first base case is going to be the most even number, which actually happens to be 0, and then the most even odd number, if that makes sense, which is actually going to be the length over 2. So as you can see, that is a2 in this particular case. So this is going to be sort of our base case here. But the process of recursion is going to keep taking the evens of the odds and the odds of the odds. And then the evens of the evens and the odds of the evens. And so it's going to keep going down the chain. And so that's where we're going to begin our recursion. So we're going to go ahead and, since I'm using JavaScript, I can do this very simply. It's just going to be it's going to be a for loop in, I think, any other language. But basically I'm going to say the evens is going to be, this is maybe some confusing syntax if you don't know JavaScript, but basically we can filter through an array where we have the element and the index of it, and we can just say if it is even. So that's I mod 2 is 0. And if that's true, then that element is going to be put into this new array. And likewise, for odds, it's going to be the same, but if the mod operation results in 1. All right, so there's a point to where we can't do this anymore, and that point is where the length of coefficients is 1. And so that's a base case we're going to check above that. So we're going to say if coefficients length is equal to 1, then what are we going to return? Well, this recursive function is returning a value. So we're going to return the first element of coefficients, well, the only element inside of it at this point. So again, the first value, this will return to 0, and the next one will be the coefficient of half the length. Well, it's not going to return 0, it's going to return the coefficients, the 0th coefficient, and the half the length coefficient. All right. And so this is going to be basically the base of the recursion up here, right? All right, so let's say that we're getting all of our evens, and then we're getting all of our odds. Well, now we need to say our evens value is going to be, and this is going to be the recursive call. We're not going to change x. And we're going to have evens, and that's going to be it for the evens values. And then odds are going to be the same thing, but with odds. Right? And we're going to return evens plus the odds. Well, times x, right? So let's think about this for a second. Let's see how this aligns. We're calling a recursive call with x squared, right? And then times x here. So really this should actually be x squared. So I'm going to create a new variable squared, and then that's what we'll send in to here. All right, and as you can see, it's automatically updated over here. We now have this recursive function that is nlogn, and it results in the same value. And let me see. Let's add some more coefficients, right? 5, 6, and 7, 8. And as you can see, they both evaluate to the same thing. And so this is the basis, the very, very basis for the nlogn part of how we're going to implement the fast Fourier transform. Because the fast Fourier transform, if you recall, is going to be a summation, right? And it has a coefficient and another number. So really it's just a multiplication of two numbers, right? But this part is the same. So the fact that we are taking some number and then multiplying two numbers, right? The Fourier transform abstractly can be put into this form. And I'll get more into that in the next video, but this is the nlogn algorithm that we're going to use to actually implement the FFT. Thanks for watching, and stay tuned for part 2, because that's when we're going to put the DFT and this recursive formula together.